So yeah, I'm going to be talking about explanation versus interpretation and how we can use machine learning techniques to, I guess, qualify our empirical conclusions. I wasn't quite sure the right term to use, but I'm going to present an opportunity that we can use and a technique that we can use to hopefully temper some of our conclusions and how generalizable they are, how reliable they are, meaningful, and so on. And as Marta said, this is almost like a part two from the last workshop, which I guess had the main motivation in it for what I'm talking about now. So I'm going to have to review a little bit of what I did in the previous workshop, but I know there are some new faces I didn't see last time, so hopefully that's not too much of a problem. Yeah, and I suppose let's get started. So the stuff I'm talking about is actually part of a paper that's under review at the moment, but there's a preprint available that if you're interested in more details, it's a little bit, there's more information in this paper than I can get through in an hour, but yeah, feel free to check that one out. And I'm going to start by saying this: social science is not rocket science, and I think I said this in the last workshop as well. The adage being that if something's not rocket science, then it's not very complicated. But actually, I think social science is much harder than rocket science. And that's one of the reasons why it's such a challenge, and it's so important for us to update our methodologies to adapt to the complexity of the phenomena that we're actually interested in. We've actually done a pretty good job of sending rockets up and down, and the tools that you need to do that are fairly sophisticated. And as an engineering student, I was taught some of those techniques. We get exposed to dynamical models and control systems, and everything's kind of nonlinear. You're very lucky if anything's linear. But in social science, despite its complexity, we tend to use very sort of blunt measures and blunt analytical tools. So I'm going to sort of argue as to why we need to improve our skill set and our analytical toolbox, and talk about some of the pitfalls if we don't do that. And then I'll present the sort of idea that I have that we've actually implemented in a few papers so far, which is just one opportunity, but yeah, we'll see. So the summary of sort of what's going on in this talk, and again, this overlaps with my previous workshop. So there are two principal modeling paradigms: predictive and causal. Some might argue that there's also descriptive modeling as well. I'm kind of lumping that in with predictive because essentially we're using these relatively sort of blunt measures of correlation and association to describe maybe low order statistics in the data. So I'll kind of lump that all in with predictive modeling. It's about associations primarily. And then we have causal modeling, which is, again, I guess just another approach, but it's more to do with fundamentally the holy grail of science, which is to understand the phenomenon, understand the mechanisms that generated the data which we observe. So it's very important. I think as scientists, we're all interested in causality, but it's really challenging, and I'll come on to some of those challenges and the pitfalls associated with doing causal modeling as we go through. So there are two interpretation paradigms, and the annoying thing about the language being used here is it's not my language. To be honest, I'm not precious about the language being used, but so long as we define what we mean. But what I tend to see in the literature is that there's this sort of umbrella term of interpretation, which is just the process of going through the research and drawing some conclusions. But then you can actually split interpretation into two sort of subcategories, one being interpretation again, and the other one being explanation. And I'll make the definitions as to what I'm going to work with for those definitions in a minute. And I'm going to argue that most statistical models that we use, and this is again, well, I'll say again from last workshop, this is 99.999% of the tools that get used in many empirical fields are not interpretable, they're not explainable, and they're not predictive either. So that's a very bold claim, I realize, and it's kind of scary. So I'm hopefully going to qualify some of that as we go through. And I'm going to suggest that maybe some machine learning approaches provide some opportunity. I'm going to argue that most machine learning models, if they're just predictive models, and we'll be talking about a predictive model, they're not going to be interpretable either. So you have to bear in mind, I'm not offering a solution for interpretation as a whole, which is incredibly challenging. Is again, the holy grail of science for me is taking causal relationships and interpreting them and sort of projecting them onto the external reality, which is high risk, high rewards kind of thing. But machine learning can at least give us an opportunity to do really good prediction. And if we've got really good prediction, we can use explainability techniques. And this is where the difference between interpretation and explainability sort of starts to come in. So in terms of the plan for today, I'm going to define what I mean by interpretation versus explanation. And then I'll give a review of some of the things I talked about in the last workshop in terms of the associational predictive model pitfalls, causal model pitfalls. These are the typical models that I see being used frequently in social science and psychology, but actually more broadly in other fields as well. There's a shift in emphasis slightly when you move towards fields like ecology, which tend to deal more with dynamics. And there are other fields that do that as well, but primarily social science and psychology. And then I'll give an overview of what proper predictive modeling means. So rather than using these traditional predictive models, I'm going to sort of inject them with some steroids and see what pops up. And that brings us on to the solution that I'm going to propose, which is this combination of machine learning with explainability. And this doesn't make an assumption that we're going to interpret something about the world. It's just going to be an explanation about the machine learning model itself, and it's going to be a very powerful predictive model. So here's the difference, the distinction that I want to make between interpretation and explanation. So firstly, interpretation, it's like the holy grail. We really want to be able to take our model and understand something about the world, external reality. And so as an example, if you had a very good model, let's say you use a linear regression, which is in my view never going to really do the trick, but let's say that you have got that model and it's correct, then you might say something like my model coefficient X or beta in the nomenclature typically used for linear regression tells me that in the real world, maybe every 1 year spent in education is associated with, or maybe even causally linked with, an X amount increase in wages. So you're making a big sort of semantic leap there associated with going from a model of the world, which is some abstraction. You're sort of doing away with some detail in order to characterize a phenomenon, and you're going from that to reality, which is this big sort of leap that you have to make. On the other hand, if you have explanation, we're talking about having a model. It could be a black box model, something that's really hard to sort of interrogate on its own. And we're going to use some explanation technique or explainer. And so here I've kind of characterized it as these dots, where each dot might represent the sort of importance of a variable being used by that model. And then maybe indirectly we can make inference about reality via this explainer, but it's still going to be a bit of a leap. Whenever we're going from our model or our analysis to reality, there's still a leap there. So we need to be really careful about what we're saying when we make that leap. But at least maybe if we have a robust explainer, then we can at least make conclusions about the model itself and what the model's doing. And it might sound, well, maybe you're an empirical researcher, you're not interested in what a model's doing, you're interested in the world, and that's fair enough. And we are going to try and make that leap, that sort of hop from model to explainer to reality. But also just in terms of fairness and decision-making processes in the world, machine learning is becoming a big thing. And so we need to be able to explain why a decision's been made. I think it's even part of EU law now to be able to justify why a particular decision has been made based on an algorithm. So it's useful for both of those things. And so as an example, I've got here my model coefficient X, and here it's the model coefficient, really emphasize the model, tells me that when the years spent in education increases by 1 unit, the model output changes by X amount. And again, this is just the case for a linear model. The typical sort of interpretation that's being used for linear models is you look at the beta coefficient and you say something about that beta coefficient. So this may actually reflect some of the statistical associations in the real world, but we're not necessarily going to make that leap to external reality. And Bordeaux kind of expressed this really nicely back in 1977, where he said that we have to really take care not to slide from the model of reality to the reality of the model. So we always have to bear in mind the limitations of the models that we're taking, and maybe that's just an obvious thing, but maybe when I go through some of the pitfalls associated, you'll realize how easy it is to slide from the model of reality to the reality of the model. So how can a model be wrong? There are two types of wrongness that I want to focus on. Firstly is in terms of its functional form. An example of this would be using a linear model on nonlinear data. And this tends to lead to some form of bias. It's usually the term being used. And the alternative is that you have a very, very flexible model, which is very rarely the case in social science and psychology because of the sort of preference for linearity and low complexity models. But the alternative is that you have a too highly complex model where you leads to something called underspecification, overparameterization, and possibly overfitting, although we have means to deal with overfitting by doing things like cross-validation, leave one out cross-validation, train test splitting, bootstrapping, and so on. And the second type of misspecification, the second way that a model can be wrong is in terms of its structure. And I'm going to use structure and causality kind of interchangeably. I'm going to argue that a structural equation model, which is a quite popular modeling technique, is a causal model, and there's no bones about it. It's designed to reflect the structure in the data according to the data generating process. So we are making assumptions about the causal structure there. And the other big point that I want to get across is that it doesn't matter how many times you replicate a study. If either of these things are wrong, that replication is only going to reinforce a fallacy, essentially. So, I thought it was kind of suited for this reproducibility society, because you can't just do a replication, even though I think replications are incredibly important. Replications actually, in light of these issues, serve to only reinforce fallacy and misguided scientific beliefs, as it were. So we really need to at least explore the possibility that maybe there's something about our model that is very quirky and unique that's leading to the results, and that again concerns that leap from the model to reality. So in my view, there are sort of three routes that we can take when we're presented with observational data. This is actually applicable to experimental data as well, but the causal inference thing takes on a particular sort of glow when we're dealing with observational data rather than experimental data. It just becomes a little bit more tricky. So if we can deal with it with observational data, we can certainly deal with it in experimental data, which gives us additional control. So these three routes include the causal route on the left here, then the typical route in the middle, which for me, I put question marks around it because I don't really know what it does. I don't really see its purpose. And then there's a strong predictive route on the right-hand side there. So let's start with the typical route in the middle. So these are typically very inflexible models. They're linear models. They don't do justice to the underlying data generating process and the complexity of the phenomena we're dealing with. There's a reason why we don't just use linear regression when we send rockets up to space, but we also have to bear in mind that humans are far more complex and stochastic and dynamic than a rocket is. And these models are typically uninterpretable as a result of their sort of inflexibility and their inappropriateness for the task. And an example of this would be multiple linear regression, which is both causally and functionally misspecified most of the time. So that's the sort of route that most people take, I think, and it's highly problematic. If we take the causal route, this is a really challenging route to go down. I see a lot of people using structural equation models, for instance. There are a couple of issues with that. Firstly, that if they're linear, then we still have that issue of functional form. So it doesn't matter that they're structured. If the functional form is incorrect, it's not going to help us. But assuming that we do it well and we have flexible functional form and the structure is correct, we can get really, really good inference out of it, and it's incredibly powerful, this approach. But it's very, very challenging. And some of the things that you might hear people talk about, and these are applicable to this causal consideration, is third variable problems, hidden confounders, but you might actually be able to say things like X influences or causes Y. And that's in the case that it's not misspecified in any way. Now, the reason why I've sort of lumped those quotations, third variable problem and hidden confounders, under causal, even though they appear also under typical a lot of the time, again, I don't really see their relevance under the typical approach because they're so misspecified in terms of the structure and the linearity, the functional form, that it's not really, it's a bit of a moot point whether or not you're worried about third variables. Again, because the model's so wrong, you're either taking a causal approach or you're not. If you're taking a causal approach, you have to consider things like the structure of the data. If you're not, then it's not, for me, an issue. It's a moot point. On the other hand, we could take a predictive approach. And I guess most of the time, I kind of see typical approaches falling under some kind of pseudo-predictive umbrella. But because they're very limited in their functional form, they're not very good at prediction. But predictive models, we might have a very flexible functional form, maybe a data adaptive functional form. We have to be mindful of things like underspecification or overfitting, but these are powerful models that can learn from the data themselves rather than having to impose our own sort of inductive bias that may be incorrect on the data. They can be indirectly explained, and I'll come on to why it's hard, that says explanation. But yeah, they can be indirectly explained. They're often, without this explanation, they're quite hard to interpret. So even though they're good at prediction, we have to go an extra mile if we want to actually use them to sort of infer something about reality or even about the model itself. So an example might be a random forest using what I'm going to show you later, which is the Sharpie Additive Explanations package. And with these models, you can conclude things like X is linked or associated with Y. And again, you might see them happen, these sort of quotes, these sort of sayings or phrases appear under typical modeling approaches. But again, because they're mostly functionally and causally misspecified, it's a moot point whether you're saying they're linked or associated with Y, because chances are your model's not good enough to actually make that kind of conclusion. So here's a brief review of some of the issues. Most of the models being used are correlation-based or covariance-based. Correlation is an extremely blunt metric, and even though it does what it does, it's not very useful most of the time. So for instance, in the situations where there's a high statistical dependence, and these are obviously caricatures, usually the relationships aren't this obvious, but in a sine wave, we get a correlation of 0. In a quadratic, we get a correlation of 0. In a toroid, we get correlation of 0. And then in this situation, sort of quad modal distribution, we also get a correlation of 0, which is what you'd expect in this situation here is actually correct. There's no statistical dependence there, assuming we're using correlation to infer something about statistical dependence. There are some alternatives though. Firstly, you can obviously fit some kind of function to your data. So you can take a function of X that's X squared, but as soon as you do that, you assume that that relationship is actually an X squared relationship. And actually very few things we're interested with are actually X squareds. So unless you're fitting it precisely for the purposes of prediction, you've just assumed that the relationship between your variables is a quadratic relationship, which is a massive imposition of structure and functional form. So we do have some alternatives. One alternative is the mutual information metric, which is much more theoretically grounded and actually gives us a measure of statistical dependence, slightly more difficult to calculate. But actually for most of the data size, sample sizes being used in empirical science, it's perfectly feasible. And so if you look at the mutual information for all of these, they're much more reasonable. This is still 0 in this quad modal distribution, 0.78 for the sine wave, 0.42 for the toroid, and then the 0.99 for this quadratic. The other issue with correlation is it's nonlinear itself. And I think this sort of gets forgotten quite a lot. And what I mean by that is that changes in correlation at low levels of correlation don't really mean very much compared with changes in correlation at higher levels of correlation. So if you look at the jump, say here from 0.8 to 0.95, that's a change of 0.15. This is quite a dramatic shift in statistical dependence. If you compare that with a bigger shift from 0 to 0.2, you're looking at noise versus noise. So here's another sort of demonstration of why we have to be very careful when we're interpreting correlation. It sort of behaves differently depending on what level you're looking at. Mutual information doesn't do that. It increases linearly with the degree of statistical dependence. So it's worth considering. And the other issue is that there's this thing called Mirage correlations. I think Sugihara refers to them as Mirage correlations. A lot of the systems that we're looking at in the world are dynamic to some extent. There's some coupling that occurs between variables. And what this means is that you can measure the correlation in 1 year or 1 day or whatever the time frame is. And if you look at it the day after, it may have disappeared or it may have even reversed. And quite often people are shocked by this and they say, oh, there must have been some regime change, some innovation in the system that's completely changed this relationship. Whereas actually what might be more likely is that you're just looking at a different point in time in a dynamic system. So these 3 graphs here are all the same system. And at one time frame, or time window, there's really nice correlation there. So you get a very high cross correlation or correlation out of that. The next time point, it reverses and you get this weird sort of intermittent effect. And then you get another example of it sort of dropping in and out of correlation here. This is a very, very simple time series that might be applicable to, say, populations of rabbits and hares and maybe lynxes and sardines and anchovies, or that's the predator-prey sort of model, but this is widely applicable across many, many domains, including things like couple dynamics when they're having an argument, or biological or ecological phenomena. So that sort of is a whistle-stop tour of some of the issues with correlation and typical models. but I also want to talk about what the issues are with structure in typical models. So this is actually the graphical model for a linear regression. And this should kind of ring some bells because you've probably heard terms like exogeneity or independent variables and dependent variables. In this case, this is kind of the case here where y is the dependent variable and we have a whole lot of exogenous or sort of independent input variables, x1 to xk minus 1. And what I want to kind of communicate to you is that that's fine, you know, that is the linear regression structure. That is actually a causal structure. And that structure is imposed whenever you use multiple linear regression. In fact, if you use linear regression with one variable, you're just ignoring the potential for confounders. And maybe there aren't any, in which case that's fine. But obviously in the case of multivariables, multivariate problems, then you have to understand that you're imposing a causal structure according to this independence. And let's say we generate some data according to this structure. So we're basically creating a simulation that's perfect for multiple linear regression. Then sure enough, you do actually recover the true coefficients. So in this blue box here, just to rush through this, the coefficients on these three variables, x1, x2, x3, are 0.1, 0.3, and 0.5. I generate some data, I run multiple linear regression, and sure enough, the coefficients on x1, x2, x3, theta 1, 2, and 3 here are 0.1, 0.3, and 0.5. So that's great. It works. It worked here because our data generating process was identical to the causal structure imposed by a multiple linear regression, which is a causal model, unbeknownst to many. And when it works well and everything's linear, we get really nice recovery of unbiased coefficient estimates, which is fantastic. But obviously in reality, we're not necessarily dealing with linear relationships, and we're also not dealing with this exogenous data structure. And some of you may be familiar with the crud factor in social science and psychology, which sort of says that everything correlates with everything. There's no exogeneity in social science or psychology. It's very difficult to sort of disentangle the structure into independent components. So for now, let's just stay in linear. Again, I'm not a big fan of staying linear. It's sort of quite restrictive and quite a large assumption. But let's say the data generating process increases in complexity. So now we've got this structure here, which is actually still a lot simpler than many SEMs that I see being used in psychology and social science, or maybe neuroscience. And so I'm going to generate data according to this structure, still linear. And these are what's called path coefficients, these numbers here. And if you wanted to say, calculate the effect of x0 on y, you can just simply multiply these path coefficients together. So -2 times -1 equals 2. So we want to check that multiple linear regression does or doesn't give us the right estimate of the effect of x0 on y, just as an example in this graph. And unfortunately, you can't do that unless you know everything about this structure and you do sort of backdoor adjustment is one possible way to do it. If you do know the structure, you can perfectly recover an unbiased estimate of x0 on y. Now, if you take a naive approach, you can get wildly varying estimates. Depending on which variables you include as your sort of control set, as it were, and they can be, orders of magnitude incorrect. And one example was given by Brady Neal, which was using systolic blood pressure and maybe some other outcome that I can't remember. But this is a sort of a medical example where the estimation of the true effect of treatment on outcome had 407% error. So it can be colossal. I mean, it can absolutely be, absolutely completely wrong. And interpreting that is obviously a non-starter. In reality, because a lot of social science problems are dealing with relatively low correlations, then you might be looking at much lower error simply because everything sort of correlates with everything. You're dealing much more with a noisy process than something that maybe has got a strong signal. But in which case you're still kind of just dealing with arbitrary numbers. So they might be very low, but they might all just be arbitrary and kind of meaningless. So these things are very common. And I frequently sort of encounter papers where I think, well, there's absolutely no way I could trust what the coefficients are and whether or not they relate to anything in external reality. So that was, I guess, a very quick tour. I think that's it. Yes, a very quick tour of what I talked about in my last workshop. And as a summary, linear models are poorly predictive for two reasons. Firstly, they're linear, functional misspecification. And secondly, they're structurally naive. The idea that everything is this beautiful exogenous structure is just not going to happen in the real world unless we take steps to achieve that. Now, causal models are great. And I didn't really explain how, but you can achieve an unbiased estimate of X naught and Y here if we know something about the structure. I demonstrated in the last workshop using backdoor adjustment according to Pearl's do calculus, but actually there are other ways to do it as well. But you still have to know something about the structure itself. And so one thing you could do is maybe do structural equation modeling. So if you actually did structural equation modeling, you got the structure correct, you would get that correct estimate. But then you're assuming you've got the correct structure, and actually it can take years to get a detailed understanding of the causal structure of a system. Furthermore, if this is assuming linearity and that the system's static, you have to trust that that system doesn't change over time, which unfortunately with humans is extremely unlikely. So you have to simultaneously be adapting your SCM to changing world conditions and changing dynamics, which is a very, very challenging task. So causal models are great, but they do need to account for nonlinearity still. You have to worry about that even in the causal domain. They make a number of strong and untestable assumptions. I haven't spoken about those. There's assumptions like ignorability, which relates to make sure that you've collected all of the possible variables you need so that there's no unobserved confounding. There's assumptions of positivity and overlap, and these make it, again, even more challenging to I guess, trust that your model is actually doing something that corresponds anything like what's going on in reality. So it makes it very challenging, but causal modeling is potentially highly rewarding, because obviously if you do go the extra mile and do your causal validation, causal discovery, and then finally start doing some causal inference, then you have the potential to really gain an understanding, a deep understanding of a phenomenon. Okay, so that was the whistle-stop tour of the workshop last time. And now I want to sort of present to you the opportunity to maybe leverage some prediction. And there's a nice paper by Tagliarconi and Jacob Westphal. And there's a quote from there where they say, psychology's near total focus on explaining the causes of behavior has led much of the field to be populated by research programs that provide intricate theories of psychological mechanisms, but that have little or unknown ability to predict future behavior with any appreciable accuracy. I think this is actually being generous. I think to say that we have intricate theories in psychology is very generous. I think most of the time the theories are untestable and vague. But they do get thought about a lot. So I'm not trying to minimize how much effort gets into thinking about them. I think the problems are just so complicated. It's often very difficult to create a testable theory. But that being said, I still think this is being generous. I think intricate is sort of presumes that there's some kind of, I don't know, value in them. I know there is value in them, but it's maybe sort of overstated slightly. And the other thing is sort of, maybe I disagree a little bit, is that near total focus on explaining the causes of behavior sounds like it's a bad thing. I think it's very important that we are considering the causes and trying to understand the underlying mechanisms. I don't want to advocate for prediction as the only thing that you do, because it doesn't actually help us understand phenomenon. It only has some utility and helps us potentially validate otherwise causal theories. So this is kind of what Yarkoni argue as well, which is that if we actually adapt our methodologies a little bit and incorporate some prediction, then we can say, well, maybe if my theory is correct, it should actually be predictive to some extent, and that would be a nice thing to check, all right? Because if it isn't, you sort of start to wonder, well, why isn't my theory predictive? You'd assume that if it was correct, you'd be able to actually predict something. But Yarkoni and Westphal are arguing that doesn't get checked enough, and there isn't very much adoption of predictive techniques. So what is a predictive technique? To sort of build it into the process here. Data analysis and explanation here, not interpretation. And this time the analysis is some kind of black box. It doesn't have to be a black box. Random forests, for instance, often get called black boxes, but actually random forests are highly interpretable because of their structure and their decision trees. But most of the time we just call them black boxes anyway, because they're still difficult to interpret compared with, say, like multivariate linear regression, which is trivially, I guess it's misleadingly trivial to interpret a linear regression. And so if we use a predictive approach, we can take advantage of all the correlations and associations in the data. We need a very powerful technique that can leverage and identify anything it needs to actually improve that prediction. As such, they have no respect for the causal structure in the data. They just do whatever they can. They're happy to use spurious correlations. They're happy to use confounders. They'll do whatever they need to do. And actually, linear models would actually do the same as this. They would do everything they can to fit. They're fit using ordinary least squares. But actually, because of that strong causal imposition in the linear regression and that assumption of exogenous structure, they don't. And they can't. They're sort of very inflexible in that way. So some examples of predictive models include neural networks, which may have billions of parameters, random forests, hundreds of branching trees, gradient boosting machines, support vector machines. There's a whole array, a whole library of possible techniques you could use from the machine learning field. I guess I kind of see machine learning as just part of statistics, but it seems to have branched off a little bit on its own. But there's lots of techniques that you can use, and all of these will sort of do, to varying degrees, fit the data more closely and be data-driven in their functional form. But what I'm going to argue is that they can be explained, but they can't be interpreted. And so the reason why I've got a picture of a cow and a camel here, which might seem a bit strange, is because a nice way to demonstrate what I mean by this is that if I were to train a computer vision algorithm to predict whether there was a cow or a camel in an image, this is an example of a powerful predictive approach. We take in the pixel data and we try and predict the presence of a cow or a camel. What the network or the model will do, if it's not causal, if it's just a purely predictive approach, is leverage every correlation that it possibly can. So any biases that exist in the data, any sort of imbalances there, will be leveraged as useful signal for that classifier. So for instance, when I present camels to the classifier, almost all the time the camels will be set on a backdrop of sand, yellow sand. Similarly, cows probably in a green pasture. And so if you were to sort of plant this cow in this desert region, it would probably predict it as a camel. It would probably be more likely for the classifier to think this has got to be a camel because there's sand than it would be that it's a cow. And that's because it's not independently reasoning about the components of the image. It's not saying, well, there's an animal and a background and I can separate them out and then independently reason about them. As soon as you start to do that, you start to build in some kind of causal inductive bias. But I'm assuming that we're just going to use these methods for now in a purely predictive sense, which is actually very straightforward to do. Sort of one-liners in R, they're not difficult to fit. But as such, they can't be interpreted because, it doesn't help us understand why it's predicting a camel in terms of the data structure externally. All we can do is maybe explain why the model's made that particular prediction by maybe looking at its activations. And it might be that, oh, I can see the model's actually using everything about the background to make a prediction, and it's not actually even looking at the camel in the image. So I can kind of do this post hoc explanation of the model to infer something about the model, but I can maybe also then say, well, maybe this demonstrates some kind of correlation that exists in external reality. And sure enough, this is a trivial example. We see this bias and imbalance in cows being in pastures, green pastures, and camels being in deserts. Okay, so I want to just now go through an example of how linearity can sort of screw us over a little bit. So this is a very simple example. It's actually adapted from a paper by Lundberg that just came out, where we have three variables, x1, x2, and x3. And what we're going to do is progressively increase the nonlinearity in the equation that relates them. You don't have to worry about the specifics, but it's kind of illustrated here in these contour plots. The Y prediction is like a binary classification problem, so it's like a logistic regression. And if the color is sort of white here, then that's a high value of Y. If it's dark blue, it's a low value. And then yeah, x1 and x2 populate the Y and the x-axes. So if we run a logistic regression and check the log loss on the model, you get this increasing log loss error in this red curve as you increase the percent of nonlinearity. So in other words, as I go from left to right with the data, as expected, as you would expect, logistic regression increases the error because of it can't adapt to that nonlinearity. That's kind of, I guess, intuitive and makes sense. If you compare that to, say, a gradient boosting machine, which is, I guess, a fairly vanilla and common machine learning approach, it's kind of completely agnostic to the degree of nonlinearity. The error is just constant there. So again, it's kind of intuitive. We might expect this, but the thing that we might not be quite aware of is that if we introduce a new variable, x3, that we make not not related to anything else in the model. So it's not related to y, it's not related to x1, it's not related to x2. As we increase the nonlinearity, the logistic regression actually assigns a lot of importance to it with increasing nonlinearity. So this red line here is the degree of importance that's assigned to that irrelevant variable according to the coefficients in your logistic model. And you can see that actually increases linearly with the nonlinearity. So not only can it not deal with the nonlinearity, but in the presence of nonlinearity, it starts to somehow think that it's using variables that it isn't. And that's obviously a big problem. If you contrast that with a gradient boosting machine, there's no importance assigned to that extra variable. It just stays at 0. It's not useful because there's no information in it. There's no reason why it would assign importance to it. So then the question kind of comes up, well, how do I know that the gradient boosting machine, being a black box, something that's difficult to interpret, how do I know that that's not using that variable? And that's, I'm going to sort of come on to the Sharpie explanations package as one way to do that. So in summary for what we've just said there, the linear model was misspecified both in terms of its functional form. Its structure was fine; it was all exogenous. But obviously, in the presence of endogeneity, it would be sort of doubly problematic. But as just a result of this functional misspecification, it was actually uninterpretable. It was uninterpretable because the coefficient attribution of importance was completely all over the shop as soon as that nonlinearity was introduced. The XGBoost model we explained using the Sharpie package, but the XGBoost model is purely predictive, so it's not really interpretable. We can't then maybe go straight as a causal interpretation. There's no structure there. It just does whatever it can. But because there was no information in that third variable, it didn't use it. So it's explainable, but it's not necessarily interpretable. So what is this Sharpie explanations package? The Sharpie thing is derived from Lloyd Shapley's game theory work, which is pretty old now. But it's been recently adapted to explaining machine learning algorithms, and I've tried to kind of characterize it intuitively here. It kind of takes the perspective that we have a model here, an algorithm, or maybe a random forest or a gradient boosting machine, and we're making some prediction. And every variable that we give to the model, every input predictor, can be sort of characterized as an agent that's trying to maximize the ability of the model to make the prediction. So that's why they're all holding wheelbarrows here. The idea is that they're trying to give information to this algorithm to help it make a better prediction. And you can see that there's a couple of variables here holding hands, and that's, I'm trying to demonstrate, it accounts for interactions as well. So it can do whatever it can. It can leverage interactions, it can leverage individual variables, every possible combination. These variables can get used more than once. It does literally anything it can. And so Sharpie takes the perspective that all of these variables are kind of collaborating together in some way to maximize the output. Over here, I've got these two people dancing. That's because presumably they're not useful to the model, so they're not contributing towards useful output. So yeah, it takes the perspective that we have collaborative agents maximizing prediction, or trying to maximize prediction, accounts for all sorts of interactions and different sort of collaborations between these agents. And the Sharpie approach tells us who helps and by how much. And this includes, again, the interactions. So this is actually a paper that I've just, I can't remember whether it's been accepted now or not. It's with my wife anyway, and we're looking at desire in women. And these are the variables that we stuck into a random forest. We did bootstrapping, we did multiple sort of runs of this. Essentially, the Sharpie package outputs various things that you can look at that are very pretty. And some of these I've included here. So this here is basically just a measure of variable importance. So for each of these variables, it gives you a measure of how important it was for the prediction. On the right-hand side, it also gives you a per data point explanation of how important a particular data point was for a prediction. So as an example, if we take, let's say, it doesn't really matter, but let's say we take partner desire here. This is a binary variable, actually. Is your partner desire higher or lower? And then the feature value, so whether or not the partner desire was higher, is 1 if it's red and 0 if it's blue. And we can see how much impact that has on a particular for making a prediction for the value for the model on the x-axis here. So this is the impact on the output, which is predicting dyadic desire. So that literally corresponds with the scale points, the scale that was originally used. And 0 here corresponds with the average level of desire. So in other words, if this was set to 1, it actually decreased the prediction for dyadic desire here for this particular variable. And you get this nice spread to see that actually some variables are very predictive, but it depends on the level and it depends on the individual. And you can start to actually zoom in on these. And I've got an example of a force plot here. So this is for one individual. It tells you how much one individual contributes towards model change and model prediction. So the base value here, this is not for our example, for a different study. And these variables, I don't actually know what they are. I know what age is, I've heard of that one, but the others I'm not sure. I think it's a medical application. So you have some base value, again, probably the average level of the model output. And then for an individual, we can see that when their particular LSTAT value was 4.98, that pushed up the model by this sort of proportion here, that's sort of indicated by these segments. And similarly, age is pushed down their prediction by a certain amount. So you can actually zoom in and look at individuals and how they impact the model. So this is all about explaining why the model does what it does. So this is really just focusing on the model itself, and we're kind of parking reality for now. But what you can do at this stage is start to say, well, maybe if these correlations exist, and these are kind of associations or correlations exist in the data, then maybe they exist in the real world as well. We're not saying anything about causal structure. We're not saying how, say, LSTAT is causally or structurally related to age. We don't know which order it comes in, whether it's mediating or moderating or whatever it is. We're just saying that it's useful. And if it's useful, then it might be useful in the real world as well. So we can start to make that leap from model to explainer to reality. But you obviously have to understand that this is purely predictive. It does whatever it can. So explanation packages allow us to sort of provide insight into the presence of associations in the data themselves, and maybe we can extrapolate that beyond the data into the real world. It gives us an insight into the impact of the model output on a per data point basis, which is very useful, especially for individualized medicine, individualized treatments. You really want to know not just what the average is, but how it affects individuals. And you can start to really dig into these individual associations. And while the use of powerful, we're also obviously going to combine them with powerful machine learning algorithms, which in turn help us to achieve state-of-the-art predictive performance. So now these models may also be of some utility. We can actually predict maybe what a good treatment would be for an individual, or what they're going to do in the future, which has lots of clinical applications. And finally, it helps us validate our theories, because again, we can say, oh, this variable is not remotely predictive, but my theory said it would be. Now there's a bit of a sort of an issue there. If you think a variable is very important in theory, you have to maybe wonder whether or not it should also be useful predictively. But then also bear in mind that if you're in a dynamic system, maybe you're just looking at it at a particular time, when at that point in time it's not. So again, all of these things have to be caveated and sort of interpreted very carefully. So in conclusion, we can take two approaches: causal, which is very difficult; predictive, which is potentially useful. It's also a lot easier, in my opinion. It's the difference between sort of running a model for a day and spending some time carefully interpreting it versus, you know, maybe decades of time trying to validate a causal structure for a phenomenon. I think in economics, it's quite normal to spend as much as a decade getting a single paper published, which is a very different process. Unfortunately, most statistical models are not predictive. They're linear, functionally misspecified, causally misspecified. They're not interpretable because of these issues, not explainable because of these issues, and replication won't do anything to help us. So we need to bear in mind that replication gets us so far, but it actually could be dangerous if you think it's kind of the be all and end all, and all we need to do is just check that we get the same result twice. If your model's wrong, unfortunately, you're just going to get the wrong answer twice. And if we do want to use linear models, we still need to consider issues. So I understand that sometimes your data are very limited. That's not a reason not to use machine learning algorithms. I think a lot of people seem to think that small sample sizes, you can't use machine learning algorithms on them. I don't really see why that's the case. But if you do use a linear model, you have to bear in mind things like structure still, very much so. And also cross-validation. I see a lot of people never doing trained test splits when they use linear models, which is actually going to seriously impact your ability to replicate that result. You need to do cross-validation, leave one out cross-validation, even if you're using a linear model. And certainly don't use any forward or backward methods for including variables according to their significance, which I see quite a lot, which is an absolute no-no, especially without cross-validating that. We can do different types of interpretation. There's the sort of goal, which is to do actual interpretation, which is pseudo-causal. Probably not possible, requires a lot of work, a lot of validation, but we can actually explain predictive models fairly straightforwardly. And if we combine predictive approaches with these explainability, then we can get best of both worlds, as it were. But it's of limited utility, but it gives us an option. I don't want to oversell it, but it is maybe an option for us to explore. I don't know if I've overrun. Oh, it's got 10 minutes left. I thought I'd bring the cow back just to cheer us up after that depressing talk. Any questions from anyone? Very happy to take them.